Sorry,
Now,
Mohammed, do you want me to share the overview of the ZK email and then you can like talk about it? Maybe that will
yeah,
save you.
yeah, yeah.
Okay,
Let's do that. Let's do that.
let me do
You
that
can
then.
share. Yeah.
Yassine, do you want me to share after you do the intro or like
No,
before?
it's okay. I just wanted to start the recording. Right now I started, so it's up to you. Sorry for the disturbing.
No, no problem.
Now it works. Now it works. Yeah. You can go. Yeah.
So yeah, let's leave it like this. Okay. Go ahead, Mohammed.
Okay. Yeah. So okay. I'll zk email. We wanted to implement it in O1.js natively using the native libraries of O1.js. So zk email works by it's basically a raw email that a normal email has a raw email version of it, which has specifies the DKIM signature. We can take the signature and prove that an email has specific components in it, or that the email at least is valid from the source. We are able to check because each email has a domain that signs it, and we're able to check the public keys of those signatures through the DNS registry. So the DNS registry is like the internet address book that we can refer to check different domains public keys. So if I see Mina.com sign something, we can see the DKIM signature, we can see the public key of Mina.com, and make sure that this domain actually did sign this message. So basically, you're able to take this email and make claim over certain components of it using regex as well. Which so using a regex circuit, you're able to search for specific things you're looking for in the email and prove that they're available. It could be like a field of your passport or a field in a formatted email that you're looking for to see like the username or specific components in the email. So the whole zkML project is like a loosely stitched together components of a regex circuit and a circuit that is able to verify the email, whether the signature of the email. Because just looking at text on its own and proving it doesn't mean anything unless you can prove that this text definitely came from that domain. So this is the zk email challenge, is to construct these two circuits or two big components that are interacting with each other. And how do you cover that as a user experience for the user? In our case, the app developer that wants to use this library, how would they use it in the most easiest way possible? We also wanted to provide backward compatibility with existing helpers that are off-chain helpers that are nothing to do with circuits that the original zk email team worked on. Because of auditability, and maybe we thought it would provide better composability with other zk email ecosystems that are using different proving systems as well. If the email format or at least the input formats are somewhat consistent across the different ecosystems or implementations. So I'll just jump in straight into like roughly how it works. I wanted to look at the Mahmoud before. I'll just go through this quickly, but can we then show the code just to run the main JS example afterwards? Let me just quickly show on the graph like what's going on, and then we can jump to it. So initially, we have the raw email, which the user is providing. It's going through the zk email helpers, which is like an off-chain component, just to parse the code and get different components out of the raw version of the email. This then goes to the next layer, which is the circuit layer, which is in green. This is the inputs that we need that will go into the circuits. So the way the signatures work, like what DKIM is really about, is just it has an RSA, just basically verifying RSA signatures inside. But there is a whole set of protocol that needs to be set upon. Like, okay, an RSA signature at its core is just a simple message signature and public key verification. But like, how do we go from email to that? So DKIM signatures is the format, is a way to have consistency across checking how an email is. So it's a protocol. It's specified in an RFC by the Internet Protocol. So it's like it's as fundamental to the Internet as anything. So we have these header signature public key these are components that are coming in this DKIM signature, which we can then use different parts of it to verify. So if you see at the bottom, we have RSA verify. It's taking the signature and the public key. It's verifying it. However, the message needed a bit of formatting before doing it, before we can verify it. And the stuff before it is the formatting, the SHA-256 hash, the headers hash, the PKCS encoding. This PKCS v15 pad is the encoding of the message, that it goes in the exact format so that RSA verify remains consistent. So you don't have to play around with it. So we're preparing the messages to it. So this is how the different components of the DKIM signature are used in circuit. I'll just maybe we can just jump to the main. I'll just quickly just show you what start with what a raw email version looks like and how it's using the helpers. We'll just run the code quickly, and then Mahmoud can dive in.
Is this what you need, Mohammed?
Yeah, let's just show the EML file. And yeah, the main TS. Let's run the main TS, which has the full flow, right? It fetches the. So yeah, we have this raw version, which is the DKIM. This is the raw email version, downloaded in EML format, and we're going to take that as our first input for our helpers, the off-chain helpers, which will use this to parse the variables that we need. It will go and contact DNS domain to retrieve the public key that we need, so that the circuits can understand what's going on. So yeah, initially we want to. This is the zk program. Can we just maybe just show the main TS? Yeah. So this is just an example of flow. Initially, we're reading the file at the top email.com, and then we're in the main function where we have the inputs. We go and generate inputs. This is a helper this is an off-chain helper, just to provide to generate the raw inputs, and then those inputs go into the email verify circuit. If you can see header, signature, public key, modulus length. This is like an RSA configuration. And these are the different inputs that we parsed from the raw email. It goes into the circuit, and then the email verify circuit just says, yeah, this is valid or this is not valid. Yeah, I mean, this is basically it. This is kind of the flow of it. Maybe we can show quickly the email verify. Okay, so the email verify takes these components. This is the input to the circuit. Takes these components, and we do the pre-formatting we talked about, like hashing the headers and then padding them, PKCS encode, and then yeah, we make it provable on this, and then yeah, we want to convert the big int to the custom big int for the RSA, so that it can definitely understand the inputs, which is what RSA verify is doing, which Mahmoud will go into in a second, about these different components of that make up the whole thing flow. So I mean, this was just an overview of the code from a top level. So I don't know, I can leave it to you, Mahmoud, now to just go through the components, because you worked on RSA, base 64 decoding, and also the regex, and you published the 3 of them as npm packages.
Yes, yeah, thank you, Mohammed. Yes, we published most of them as npm packages. As you can see here, we have O1JS RSA package, which is a standalone package from the PR done by the O1JS team. And this is also the O1JS base 64 package that is used in here to base 64 decode the body hash. So, okay, let me go through the graph again. So, as you can see here, the body hash is taken as an input, but it's not the case. We actually is part of the headers in here, and then we fetch it from regex. So I will walk you through regex example, how to fetch a body hash like that. And as you can see here, all of the green bubbles are the circuit inputs, and these blue rectangles are also npm packages. So except of course the SHA-256, which is a gadget from O1JS. So for the midpoint milestones, we basically did base 64 decode partial hash. We did also prototype, as Mohammed described, for zk email, and we also have RSA verify. So one also thing to point to is that, as you can see in these like these small bubbles, body hash check, modulus size, these are not provable types. So modulus size is a number. It's not a provable field, for example. And body hash is a Boolean, it's false or true. Because you have the option to whether check the body hash. If false, then you will ignore it. And if true, then you will go through this whole section where you do base 64 decode, partial SHA, and assert equals, and also like, as you can see here. So this is like a different block, which is optional. So let me go through base 64. So go. Yes. So in here we have yes. So recently the zk email team basically did base 64 decode, and this is wrapped circum code into O1JS, which is also quite functional. And now, like a few days ago, I just did a PR trying to merge these base 64 utilities into the main O1JS. So base 64 decode works well. We can do npm test here, and I'll show you the tests. But we also like it's equivalent to what you can do also with encoding. Why? Let me explain this. Because in this graph, you will have the body hash as base 64 encoded. And what we can do is to decode it, take the plain bytes from the hash function and assert that. And equivalently, what we can do is leave it as it is as base 64, and then encode the body hash from here as base 64 and assert both base 64 digests. So that's why we added encode in here. So an encode is more efficient than base 64 decode. And why is that? Because this is a bit tricky to show. We have lookup tables because these base 64 operate on ASCII. Because, for example, in a test like this, so this is a base 64 input. So it's meaningful when you want to encode or decode this in base 64. So, but it's not the case if you have this as bytes input, which are UTF-8 bytes inside the circuit. This is why we need base 64 decode and encode inside the circuit. So, and this allows, I think this is gonna be very, very useful for other developers to use this on Web 2 protocols that they encode base 64 some text or some inputs. Yes. So to assert that our work is functional, we also in here in the test function, test base 64 decode, we are using some native JavaScript base 64 functions to assert that, and all of them work really well. You can see here we have 1,000 iterations for decode and encode, and all the tests, as you can see here, are functional. I wonder if I have the time to walk through everything, but next let's go through RSA. Yes. So RSA was work done by the O1JS team, which was like an old PR that it wasn't tested, and that's why they kept it as a draft. And thankfully, we used that as like the foundation to build on top of it. So what we did is that we added tests in here. We added some RSA, random RSA parameter generators to check that the work is fine. And what we realized is that there used to be a like small bug when calculating the limbs of begin, provable begin. That was like taken pretty positively from the O1JS team. That made us like happy, and they took the work, took the tests, and then they did like they refined the code, and then they pushed the PR. And I think it was 101, I think 101 release of O1JS. So, and this is RSA. It works for, you see, as in here. I'll go through the README. They kept all the notes. You can go through them. So here is that we have begin 2048, which takes any input up to 2048 bits. So if you are doing also RSA on 1024, 512, which is not secure, but I don't recommend doing it. Yeah, you can do that. Now, also, you can see these in the tests. So if we go again to the tests, we have this is hard coded. We have so 1 second. Yes, so we have 512 in here. It works. 1024. We have 2048 with different iterations. We also like doing some unhappy tests or to reject some overflow inputs or anything of that sort. Also, like you can see some preview, so all the tests run. You can also see some preview on what to expect about the rows of RSA. So this is like constant time because like it's the same for whether it's 1024 or 2048. Maybe in the future there will be an optimized solution for this, but it's really, really optimized compared to what Circom and zk email did. It's like 150,000 R1CS constraints. On the other side, in here in O1JS, it's amazingly low, like it's 12,400. And as you can see, compile time, proof time, verify are really slow. So this is for RSA. Let me go fast also through the regex. So as I described earlier, that we are taking the body hash as an input here, but it's not the case because we are taking it from headers. And let me show you. So as you can see here in the EML file, the headers are like this section. And the body hash that is the true value is this one, exactly this one. So what we want to do in case we want to check the body hash is that we fetch this with regex, then we base64 decode, and then we calculate it ourselves as in here. So this is what we are doing in here, body hash check, decode, calculate the hash, and assert. And let me go like walk you through a demo on how to do it with regex. So this is pretty cool. So what I did in here is that let me show you how to use the compiler. So okay. So the base64 regex for the email is ph is equal. Then we have the base64 regex, and we have a plus because it's repetitive. And what we need to do, this is the amazing thing about the regex, is that we only want to reveal this part. We have to skip ph equal and also the column in here. So, and as you've seen here in the command, we have 5111. And why is that? Because we need the transitions. So let me copy this one. This is how you use zkregex. And let me go here to the browser and come here to the cool utility. And I do Control V, submit, and I can see the states here. So we have ph equal 5111, which is the base 64, and a column. So what we need to reveal is only the 5, 1, and 1, 1 transitions. And this is why we did this in here. And if I push enter, then I get this circuit compiled. I take it like this. I copy. I come in here. So I will replace this. I come in here. I paste. And then what I did. So all of this is UTF-8 bytes. So I just added some utility function in here to log it again in string. So I took a chunk of the headers, and as you can see in here, the correct value is this one, right? And this is a huge string, by the way. Like, and we are doing all of this inside the circuit. Imagine, like, this is revolutionary because we are scraping some text strings inside the circuit in O1JS. What we did is we did the body hash regex. We took the bytes from the input, and then we revealed the bytes because this is 0. And then I changed the revealed bytes into a substring. And then it's gonna log again the input from here. So let's see that. So you see, this is the revealed input. It's the same as this one, which is really, really amazing. So we will bind this feature in the main zkImail repo very soon.
Let's talk about the let's just talk about the milestones and where we are, like, so that everyone just so we can wrap up like what we've done so far and where we are in the roadmap, so that everyone just knows where we are.
Sure. So for the mid milestones, we reported that we will be doing the basic. So we did the research about zkImail, and this is how we adapted the helpers to parse these inputs, as you can see here, and as you've seen also in the prototype. Secondly, what we also reported in the mid milestones that we're going to publish RSA package to do the base 64 and also the partial SHA-256. So I hadn't the opportunity to show you the partial SHA-256, which is one of the milestones. But first, we claim that it's the dynamic size SHA-256. So that work is already there, and I have a PR in almost ready that I can push that helps you stream some stream input bytes into the SHA-256 O1JS gadget. The thing is, that's not what we really need about. So that's ready. We will do that because it will help the community of developers on Mina. But what we really need is called partial SHA-256 hash. It's different. And how is that? So as you know, in SHA-256 and O1JS takes 5,000 rows, but that also multiplies whenever you have bigger inputs. It goes like chunks of 256, 32 bytes. So imagine if we have an input, which is one block, and then you have a second one. So instead of hashing with 5,000 rows, you'll have 10,000, and so on, 15, 20, 25, 30. And if you reach the limit of 2 to the power 16 of the limit of rows, then the zkImail circuit would be unusable. And this is also an optimization done by the zkImail team. So, and what it does, it says, okay, we know that you have a big input, but we don't want to hash the whole thing. Just prove to us that you have a chunk of the pre-image that you want to hash inside the circuit, aka provable. So what it does is, let's say, imagine if we have 5 blocks, as in green here. So imagine what it does is that you hash these 4 blocks outside the circuit, and then you just keep hashing from this point. And this way, you will keep hashing constant size of 5,000 rows inside the circuit. And this innovation, when published, will help anyone who wants to use SHA-256 or any other binary hash function inside the circuit. So this is what's our plans, what's happened with the mid milestones. And next, what we will do, I will update you briefly. We will finish this. We have it working.
Do you have
Yes.
the milestones on the screen, like, so we can just show it, like the mid milestones?
Yeah, sure.
If it's easy for you to.
I mean, I don't have it, but I have to look into it.
Okay.
But I hope this is clear because I mean, yeah, the blocks here are like quite clear, I think. So mainly the mid milestones. You can also verify this on the page, as Mohammed said. So, yeah.
I posted it on your Telegram. Just you can open it. If it's open. If it's not open, it's fine.
Yeah. So I think I assume you can see this. Yes. So so for the first milestone, first we planned regex compiler to be as advanced, and since we didn't get that opportunity, I did that as standalone from the Navigators program, thanks to the Mina Foundation also. So what we did is not hard-coded example for zkImail, but rather, as you can see, it's a generic compiler for any regex pattern you want to do. So, and we also did RSA. So upgradable SHA-256 is complete, which is also called the dynamic SHA-256. That's done, but what we need is something different. It's almost finished, but we will publish that very soon. Base 64 tests for RSA and are done, and the test for RSA is what made it possible for the RSA PR and OpenJS to be merged. So as I said earlier, regex was supposed to be hard-coded, tailored example for zk email, but we did it generic, and as I showcased an example on how to do that. So yes. And later, this is the whole milestone of the whole project. So we will do 5, 6, and other works of optimization. So we have to integrate in the second half of the zkIgnite is that we have to optimize because it's heavy constraints. Well, that's why we added base 64 encode rather than decode. It saves 400 rows. That's why we need to complete the partial SHA. And also, like, we need to do some zk apps that contain some domain public keys to check the integrity of that. And when the work finishes, we will publish zk email as a package. One other thing we will do is that we have some utility for regex it's called select regex, because regex fetches all the bytes that are accepted but leaves 0 bytes inside. So we have to clean that. And once everything's ready, we will publish this as NPM, as I said, and we have a detailed documentation. And it would be also good to bind this to the existing work of zk email because they also did an amazing job.
Yeah, we can maybe leave it for questions now if people have any. Wrap it up.
Thanks, Mahmoud and Mohammed. Any questions from the crowd? Yes, Harish, please.
Hey guys, thank you very much for the presentation. I have a little difficulty understanding on how the regex component is used in the flow. Could you please elaborate? Is that something which a user needs to like generate, compile, and then feed into a verification? Or is this going to happen automatically, I guess, when you're trying to prove any email?
Okay, so yes, thank you for the question. So regex, if you are familiar with regex in JavaScript or any other programming language, it's the same as you can do in a circuit. So this body hash is input, but it's also part of the headers. So let me show you the EML file in here. So how is regex done? So imagine, so this is an email EML file, raw email file. But what I want is, I want to fetch this input. Or let me say, we can also do a regex to fetch the timestamp, for example, which is, let me check. Yeah, this one. So with regex circuits, I can just give it the patterns. So I can do the pattern for 2 numbers next to each other, space, month in here, or any alphanumeric that starts with capital and then ends up with lowercase. So I can do like just tailor some pattern that I want to scrape from the whole input, because this is the whole input for the circuit as well. So what I do, as I showed you in the compiler, is that I choose my own regex pattern, and then I select something to reveal inside, which is this one, for example. I choose the regex to fetch the body hash, and then let me show you. We didn't add this in here, but let me show you. So normally it's so body hash. So so you see the header body hash. Normally we do it like this: const. We remove it from the inputs in here. We remove it, and then body hash is equal body hash regex, and then we know that it's part of the headers in here, and then we give the headers as input to the regex. So headers, and then we should take bytes, not fields, not uint8 arrays. And this way, we will fetch this from the headers. And why is that important in the case of zk email? So is that we know the headers because we validated this in the signature. That means our headers, the integration check is valid for the headers. And then the second step is that, okay, I also need to do the body hash, but I don't want to trust you to give it to me as an input. And this is why regex is pretty important, both as security assumption in here, is that I take it directly from a header, which is part of a verified signature. But more elaborate reply to your question is that, yes, you can use it in any implementation, in any bytes input in a way. So yeah, and this is how you use it. So you have a huge input that you want to reveal some substring from.
Yeah, I would just say conceptually, Harish, like if you are an app developer, so the app developer would be using this compiler, and each app developer would have his own thing they're trying to verify. Maybe it's like to verify Twitter ownership. So they will design it. So you need to design the circuit, that specific circuit that would look for the specific strings in that Twitter email format. That's why whenever an email format changes, you have to as an app developer, you have to recompile, generate this new circuit that would do it. That's actually one of the weaknesses of zkImail in general, from an app development point of view, is that every time the email format changes, which could be susceptible to like maybe simple marketing kind of changes to the format, and that could affect something fundamental. That's why like there's a direction towards also APIs or signed APIs, if that's possible as well, as a form like more stronger guarantees on data structure. But at least this regex stuff allows us to do it today now. That's what's cool about it.
No, it's awesome. I think I got a little confused because Mahmoud pasted a pattern and it generated this circuit code. I wasn't sure at what point this gets added to your main circuit, which is used in the verification of the email. But I feel I understand it a lot better now.
Okay, so beforehand you choose the pattern you want to fetch, because like any email header has this ph is equal to something. This is how you prepare. Let's go through the command again. So ph is this one, ph equal, and then az, and then it's like it takes alphanumeric, lower and uppercase, and then digits. It also takes some, as you can see here, forward slashes and equals as a padding at the end. And this is the pattern we have. And a plus is for repetition, because so I know beforehand that a certain pattern would exist. So and this is how I do it. On the other side, you can not only fetch in here, you can validate. And the circuit in here, and we have this out, which is bool. And then you will do assert to true. Why? Because first, this check will tell you that a pattern is found or not. And then if it is found, then you can also reveal in here. But in the case of validation, this is called scraping. But in case of only validation, you will do, instead of, I can remove this reveal substring and only give it like this. And it will be, as you can hear, only out. It will remove the reveal.
Gotcha. Thank
Yeah,
you.
I think it's clear, Mahmoud. We can maybe leave. Yeah, see if there's any you guys.
Okay.
So I think we have one more question in the chat.
Yeah, good question. So regex is very, very important for such applications like Twitter. So, and how is that? So once you verify that the email is valid, and then what you do, you go to the second check to verify that the body hash is correct. And once you do that, then if you do that for Twitter email, you will get, as you can see from the original work from zkImail, is that you will have a line at the end in the body that says this email is meant for this user handle. And what we will do in that case is that we also add regex to fetch the user handle. And this way, the proof of Twitter will fetch the user handles, and you can use that for different application. For example, any user that's got this Twitter can do this.
I think like IMDev, you're referring to like if why would the format, like if the format changes, I'm assuming something like that. and we can just check that the email came from the domain, and that should be sufficient. But it's like it's going to be dependent for each app, what format, because how we different emails are for different things.
Yeah,
We need to check the
that's
body.
true. Yeah, that's true. So yeah, zkImail does not support everything so far, including the original work, because there are many differences in how they take the inputs.
The
But-
interesting thing is if we have APIs, it works. Like if we have API, then it's just one domain, right? Like you can just put one thing on the. I don't know if that would work even. Actually, I take it back.
Yeah,
But
it
I've
works.
shown you the
It's a matter of integration at the end. Yeah,
Yeah.
but it's delicate. It's very delicate.
And Dave says they all love to use this project. Right. So if any more questions, then we'll. Okay, then yeah, big thanks to Mamun and Mohammed. I think you have been doing great progress as well. So I'll just
Thank you.
stop this one and then